Hello and welcome to today's webinar presented by Dlubal Software. Today you'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is CSA O86 2014 CLT design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Bastian Kuhn will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So as far as the content for the next hour today, I will review the initial model that I've already created within our main program, RFEM. So this includes a basic geometry as well as a loading. Then I want to explain how this add-on module RF-LAMINATE works within the main program, RFEM. Then within RF-LAMINATE, we'll go ahead and input in our CLT data. This includes composition definitions as well as stiffness adjustments, the adjustment factors directly from the CSA standard, as well as serviceability design. Then we will run our full analysis and design according to the CSA O86. And throughout the presentation, as well as at the end, I'm going to give you additional modeling tips and suggestions. This includes how to deal with singularities. So we can jump over to our program RFEM, and as I mentioned, I went ahead and have initially modeled this structure here within RFEM. If you are curious to know about the basics of modeling, we have plenty other webinars as well as introductory tutorials and examples available on our website and YouTube channel that really go over the basics of how we could get to this point. But for the sake of time, I have modeled this structure here, and I have also applied some basic loads. But you'll notice that the entire structure is this gray color. And if we click on any one of these panels, you'll see here that the material was defined with concrete. So with the process of modeling a CLT structure within the main program first, we just need a simple placeholder for all of these panels. And concrete work, steel, it doesn't matter, as well as the thickness doesn't matter, because eventually within the RF-LAMINATE add-on module, we're going to override this material with our true CLT composition details. So for now, we just have our placeholder here of concrete. You'll also notice that I have some beam members within the program as well as columns. So these are just typical glulam members. For example, we have these beams here that will be holding up certain portions of our CLT ceiling up at the roof. And what you'll find when we turn this into wireframe view is that 1D members are represented by 1D line elements. And so inevitably when we turn this into the rendered version here, you can see that the center line of the beams lines up with the center lines of the CLT panels, when in fact we'd actually like to drop these glulam beams below the CLT panels. And we can do this by applying a new eccentricity. So how I can do this is to select all of these members at my roof level. We can right click to edit the member. And under the second tab here, I have options where I can define a new member eccentricity. So inevitably, I could go ahead and manually type in the eccentricity distance. I'd like to drop this beam below the panel by considering half the depth of the beam as well as half the thickness of the panel. But the problem is that if we make any changes to the panel thickness or the size of the beam, that I'll have to go in here and manually adjust that eccentricity distance again. So rather, it's useful to use this automatic option here where we can line up the top of the member and offset it from the bottom point of a surface. So I can choose the top of the beam. I can graphically choose any surface at my roof level. So we'll choose surface number 63. And I'll choose the bottom point of that surface. So now when I click OK through these dialog boxes, you can see those beams now drop below the panels. Now the benefit of this is that when we go in and we adjust the true CLT properties, the thickness will be changed from what we currently have at model, but that eccentricity distance will automatically be adjusted. Now we want to do the same thing at the first roof or the first level here. So I'm going to hold down my control key to highlight all my beam members at this first level. I can double click to activate this edit member dialog box. We can create a new member eccentricity, and in the same manner I'm just going to take the top point of the beam and I'm going to offset it from a surface, but this time I'm going to choose a surface at this first level, surface number 71. We choose the bottom point of that surface, I click OK, and now you can see that those beams were dropped below those panels as well. Okay, so essentially the basic geometry is complete. I did want to show that I have applied a few loads to the structure. So you can see here my dead load. If we activate the loads graphically, just simple surface loads on both the roof and the first level. We can take a look at live load, exact same concept. Maybe we've just adjusted our magnitudes here. A snow load, which is just activated on the roof level, and then a simple lateral load for wind, which is applied in the global Y direction here. So when you first create a model, I'm going to reactivate this dialog box by right-clicking on my model name and going to General Data. When we first create the model, or we can go back into it as I just showed you, the load combinations will automatically be created according to the standard that I've selected within this drop-down box. So you can see here the NBC 2015 was selected. We also have the ASCE 7 2016, as well as many other international codes, including the Eurocode. When this checkbox is checked, those load combinations will automatically be considered by the standard that you've selected within this dropdown. If we uncheck this, then we can manually create our load combinations and this standard will be ignored. So taking advantage of the NBC 2015 for today, I can launch my load cases and combinations dialog box. And once again, we can see our simple load cases that we've defined here. But under the combination expressions, the program's automatically going to generate my strength load combinations per the NBC 2015, as well as my serviceability load combinations. If I'm curious to see what those are according to the standard, I can click my info button here to see the load combinations directly from the code. Now, most importantly might be the load combinations tab, though, where we can see these load combinations listed out individually for strength as well as serviceability. And this is based only on the load cases that I've defined under that first tab, which includes dead, live, snow, and wind. Now, all load combinations are calculated according to a second order analysis by default, considering both result combinations here, and that would be available on the next tab. And a result combination is nothing more than an envelope solution. So it will consider all of these strength load combinations considered here on the right-hand side and give us the max and min for deflections, internal forces, support reactions. Same thing with the serviceability result combination as well. So now that we have those load combinations defined, we can view them here graphically, which will include all the dead, live, wind, and snow loads shown on the structure here. And you would think that, okay, we must be fairly close to running an analysis, but remember we still have all of these concrete panels defined here rather than our true CLT panels. So this is where we want to launch the add-on module RF-LAMINATE. And the add-on modules can be found within the project navigator over here on the left, and you can see this long list of add-on modules. This is why we have the concept, just only pay for the modules that you need. It keeps the cost down for the software as well as cater to your specific projects. So we can launch RF-LAMINATE here. The add-on modules are also available within this drop-down box at the top, and we can find RF-LAMINATE under Others. So when I say add-on module, it's nothing more than just this simple dialog box that pops up within our main program RFEM here. So let us jump back to the PowerPoint to discuss exactly how this add-on module is working with our main program RFEM. So pretty soon we will go ahead and define the individual layers for our CLT compositions. And each individual layer has its own stiffness matrix based on the modulus of elasticity and the shear modulus. And we can see a simple example of a single layer stiffness matrix here. So what this add-on module is going to do for us then is consider all layers together to create much more of a global stiffness matrix for the panel itself. And you can see here an example of the D11 entry, for example, for a single panel. Now we're going to take this overall stiffness matrix and we're going to export it back out to RFEM. So instead of seeing those concrete surfaces, we'll now see the true stiffness of these CLT compositions exported back out to the structure. We can run our analysis to determine what the internal forces are on these panels. Well, we're going to take these internal forces from the main program RFEM and we're going to bring them back into the add-on module in RF-LAMINATE. And the stresses are going to be distributed to each individual layer of the CLT composition. And a stress distribution for a cross-section of the panel might look something similar to this. Now, even furthermore, when we take these stresses and we distribute them to each layer, we're going to separate them into tension, compression, bending, shear, and even torsion components. And we're going to check these stresses in comparison to the design strength set forth by both the material as well as taking into consideration the CSA standard to eventually give us a stress design ratio. So that's what's going on behind the scenes, and that's why we want to take advantage of this add-on module for CLT. So the first thing to do when we are within this add-on module is to choose our standard. And you'll notice here that we have just added the CSA O86. So this is the module or the standard we want to take advantage of within the module today. We also have the NDS, both the 2018 and 2015, as well as European standards. So we want to select the surfaces that we're interested in design. So for today, perhaps I'm only interested in the top roof panels, so I can graphically select those, as well as maybe a few wall panels here. So I'm not designing all of the surfaces. I'm only interested in designing these few that I've selected here. As far as the ultimate limit state, I want to choose all of my strength load combinations and move them over to the right so they'll be considered for design. Then I have my serviceability limit state where I'm going to choose my serviceability load combinations from the NBC 2015 and move them over to the right-hand side. Now keep in mind all this information for our load combinations was brought in from the main program RFEM. I don't need to redefine any of this. Then we just simply move down the list over here on the left. So the next table here is our material characteristics for our CLT compositions. I want to rename our first composition to floors. Now, what I can also do is select the surfaces that I would like to assign this composition to. So remember, everything is defined as concrete right now in our main program. So for our floors, maybe we select the roof panels. We also select the first level here. And then now this composition will be assigned to all of these surfaces listed here. We also have the ability, if you'd like, if you want to change the color. By default, the color is blue, but maybe we want to change it to more of a wood color. So we can change that color here, including the texture. Then under the layers, well, this is where I individually define the different layers for my CLT layups. I can click on these three buttons here, and what this will allow me to do is to pull open the material database that we have available within RFEM. And over on the left, I can filter to timber, I can filter to Wood North America, and underneath this we have both the AWC and the CSA. So all materials are available from the CSA standard. If we just choose any arbitrary material, we can see the material properties are presented to us here. We click OK. We give our first layer a thickness, so maybe 1.5 inches, and the first direction would be 0 degrees. You can see all the material properties are also listed within this table. So our second second layer would be defined in a similar manner. We can choose that same material if we'd like. We keep the same thickness, but this time the second layer would be oriented at 90 degrees from the first layer. Now this is relative to the local x-axis, which we'll get into a little bit later. So once you create your custom layups here, you do have the ability to save them into the library and open them up for a future model. We also have the ability to take advantage of the imported layers from our library already available. So when I activate this option, you'll notice that the producer dropdown has quite a few producers already available. You'll see many European producers specific to North America. You might take advantage of Nordic structures, Smart Lam, Structure Lam. Today, we also have the PRG 320, which we can utilize for Canada, just for example purposes. Then we choose the type here, which we can choose grade E1. Then we can choose the thickness, which we'll select 105 millimeters for today. And we have our 3 layers generated automatically. So when I click OK, the materials, the thicknesses, the orientation are automatically brought into this table for me based on that specific producer. The other thing that we need to discuss before moving on, though, for this composition is the composition details that we can find with this dialog box here. So this is actually fairly important for the analysis in order to get accurate results based on the materials and the products that you're using. You'll see here a few different options. Consider coupling. We have the CLT without glue at the narrow sides, as well as shear failure, which is in relation to torsion design. Then we also have these stiffness reduction factors. So I'm going to go back to the PowerPoint to explain this in a little bit more detail. The first option for consider coupling, this is automatically checked by default. You can see over on the left, when we have coupling turned on, we're assuming that we have glue at the top and bottom of these individual layers, essentially coupling each layer to each other. So when we look at the stress distribution, according to normal stresses as well as shear stresses, we're going to see a common relationship here between all of the layers. But in turn, if we uncheck this option and we're not considering coupling, we're assuming that there is no glue coupling these layers together. When we look at the stress distribution, well, we're going to see really independent behavior for each layer. The second option here, cross-laminated timber without glue at the narrow side. So this is fairly common with most manufacturers. So likely you'll end up checking this checkbox on. This is assuming that we do not have glue at the narrow side. So if we take a look at maybe an exaggerated cross-section here of a CLT panel, each layer includes individual board elements. And with this checkbox turned on, we're assuming that there is not glue between the narrow sides of these boards adjacent to each other. Therefore, when this checkbox is on, we're automatically going to set the modulus of elasticity in the local Y direction of the panel equal to 0. So we do not have any stiffness in that direction. Now, it's highly recommended that we also make an adjustment to our stiffness reduction factors K33 and K88. So we'll move on to the next slide to discuss this a bit further. So K33 is for the torsional stiffness of our panel. K88 refers to the in-plane membrane stiffness. Now, quite interesting enough, neither the CSA standard or the NDS standard really discuss what to do about stiffness reductions in the event that we do not have glue at the narrow sides. And the Eurocode, the EC5, in particular the Austrian Annex, has equations that do go on to discuss exactly what should be done for the stiffness reduction factors in the event that we do not have glue. So I would say that it is highly recommended. We can refer to the EC5, which we'll be doing for today's example, but of course you want to take this by case basis. So I have just a simple Excel file on my computer that references these equations from the EC5, and you can see that I just need to input in the total thickness of my panel, which is 4.14 inches, the number of layers is 3, and my approximate board width, which is given to me from the manufacturer, is 4 inches. Now, from these equations from the EC5, we'll determine that K33 is equal to 0.435. Well, this is the information we want to put into the torsional stiffness reduction here, K33, within the program. Same exact concept for K88. We determine it's 0.533. This is the information we would input then into the add-on module for the membrane stiffness reduction. Now, some manufacturers implemented into the program have already given us this information. So you will see that reflected if we do have it available, but if not, then maybe it's something you want to consider inputting in manually. The third check here is for torsion considerations, and it is shear failure in the glued contact surface. Now, this is mainly for wall elements loaded in plane. So perhaps a floor element, we're not so concerned with torsion, but a wall element, we certainly could be. This check, this torsion check, is only available when we do not have glue at the narrow sides. It is recommended to set the FE mesh of your wall elements, or whichever panels you're checking for torsion, approximately equal to the board width. Now, once again, the NDS as well as the CSA standard do not give any information related to torsion for CLT design, so we're referencing back to the EC5 for these interaction equations. And you can see the interaction equations displayed down here at the bottom, which are made up of 3 terms. The first terms can be viewed over here on the right on the top. The second terms can be viewed down here at the bottom. And the third terms are just simply the shear stresses, which are taken from the internal analysis from the RFEM model. Now, torsion, that particular check is not turned on by default within the add-on module. So you can see just a quick screenshot, which I'll show you in just a minute back in the in RF-LAMINATE, exactly which stresses we can turn on and off. Torsion is not one of them. So you want to go in here and activate this. You can imagine that if we turned on all of these different stresses, it would be very overwhelming. So by default, we leave the stresses that we have determined are most important for design activated. So we'll do that in just a minute, as I mentioned. Okay, so going back to the add-on module here, as I mentioned, we're working on our floor elements. So we do not have glue at the narrow sides, but I'm not so concerned with torsion, so we'll go ahead and turn that off. Now, according to that Excel document that I just showed you and the EC5 equations, we will reduce K33 to 0.435. And I will reduce K88 by 0.533, and I can click OK. So that essentially defines our first composition for our floors. But now we need to create a second composition, and we can do so within this same table. This time we will call this one walls. Once again, maybe we want to quickly just change the color here to something more like timber. And I can choose my surfaces by graphically selecting all of my wall elements here. I click OK, all of the numbers are automatically populated. I'm going to import in my layers once again from the library, and you may want to adjust the type, the grade, the thickness for your walls, but in our particular case today, we'll actually use the same type and thickness from our floor elements. So I click OK, my layers are automatically populated. I want to go into my composition details again because what we have set at default is not applicable from the manufacturer I want to use. So I want to activate that there is no glue at the narrow sides. I also want to activate my torsion checks. In this case, I want to put in a plank width of 4 inches. I once again will reduce K33 to 0.435 and K88 will be reduced by 0.533, and I can click OK. So just like what I mentioned in the PowerPoint, if we click our cursor within one of these layers, we actually can view the individual stiffness matrix for that layer. Right next to that, we can view the global stiffness matrix for this composition. So you can see the numbers are already input in here for an entire stiffness matrix, and this is the information that's going to be exported back out to RFEM. On our next table here, material strength. So we're currently looking at our walls, and we can see here the available strengths for bending, tension, compression, shear, as well as torsion. When I change this to my floors, same thing. I have bending, tension, compression, shear, but you'll notice I do not have an available strength for torsion because we are not checking that for our floor elements. Now, these numbers are simply based on the material strengths given to us from the manufacturer, but because we have selected the CSA standard, we're also going to apply those modification factors directly from the code. So you might be curious to think, well, which modification factors are exactly being applied? Under the standard button here, we can view this general tab to take a look at exactly which modification factors are effective with these strength designs. And specific to the CSA, we will see the load duration factor, we have resistance factors, and then we have an additional modification factor, K-mod. So what I'm going to do is I'm going to jump to the PowerPoint model, and go ahead and explain in a little bit more detail about these modification factors. So within the CSA standard, the O86, there's certainly quite a few modification factors available. But what we have done is actually simplified quite a few of these within the RF-LAMINATE module, and there is a reason for this. For example, the system factor, KH. The code tells us in Chapter 8 that this should be set to 1.0 for all strengths. The service condition factor, the code specifically states that CLT should be used only in dry service conditions. So we're going to make the assumption that K sub S is equal to 1.0. Treatment factor, we assume the CLT is untreated. Now, the other three factors here are a little bit different. The CLT bending moment factor, size factor, slenderness factor. So the CSA standard really takes an approach for CLT design as though it's treating it like a member. And this might be extremely beneficial for hand calculations, just to simply run a design check. The problem with that is, in a finite element analysis software, that 2D surfaces are truly surfaces. We do not treat them as members. So for example, the bending moment factor, we have no differentiation between the strong and the weak axis for a 2D surface, so we cannot apply this factor. Size factor, slenderness factor, again, these are specific to members. We cannot apply them in the module to 2D surfaces. We don't do buckling checks, for example, where we determine what the member length is, so to speak, or what the dimensions are. So if you have the situation where you do not have one of these factors equal to 1.0, that's okay. All you need to do is to simply adjust K mod, and this is the modification factor that can be applied to all strengths within RF-LAMINATE. So again, the assumptions over here on the left for these modification factors are made as 1.0. If you have anything else, just go ahead and adjust K mod, which will modify those design strengths. So we can go back to the RFEM model here and back into RF-LAMINATE. You can see K-mod available to us here if we want to make those changes. Now for today, I won't be doing that, but I did want to point that out. The load duration shows us the load duration factors. We have some defaults set here, but you can use this drop-down box if you want to make changes to the load duration factor. Now finally, we have serviceability data. So this is our deflection checks. If we are only interested in deflection for our floor panels and not our wall elements, all I need to do is to graphically select those those floor panels graphically within the model. I click OK. Now notice that the reference length is available in the drop-down box here as the minimum boundary line, the maximum boundary line, or it can be user defined. So in this case, we'll use the maximum boundary line. Is it a cantilever? And what is the deformation relative to? Is it the absolute or relative deflection? And for a little bit information on these drop-down options, you can refer to this picture down here, which explains it in a little bit more detail. So we might be curious to know, well, what exactly is the limiting deflection ratio? That is controlled under the standard options. Once again, you can find it under serviceability limits. And depending on the design situation, whether that's live, permanent, or total, we have our limiting deflection ratios that we can set. Now, these design situations are controlled, if you remember way back when, under the General Data tab, we moved these serviceability load combinations over here to the right. Well, you can see that within these load combinations, we can set whether this is live, permanent, or total. So maybe for our design situation today, we will set all of our load combinations for serviceability to permanent. So now our limiting deflection ratio will be L over 360. So when I click OK and I go back to the RFEM model, you'll notice here that my structure is no longer gray for concrete, but rather we have these timber colors because we have exported out the true CLT properties. And if I double click on one of these panels, I can see the stiffness is now set to laminate. The material is set to RF laminate, which it's grayed out because all of that is controlled within the add-on module itself, including the thickness. We can even view that global stiffness matrix here within the details. Again, this is the exact same information that you would find within the RF laminate add-on module. So we might almost be ready to run our analysis, but we have one problem, and that's that every joint within this model right now is a fully fixed connection. And for any of us who have done CLT design or timber design in general, we know that's typically not the case, that these CLT panels will likely be joined together with the use of screws for our connection. Well, with the screw connection, maybe we want to release the moment completely and to account for some type of slip with the screws as well. The same goes for the connection of our members. If you remember at the beginning of the webinar today, we dropped those members, those glue line members below the CLT panels. Well, we probably don't want to consider a fully fixed connection between the panel as well as the member. So what we want to do is to begin addressing this by taking a look at line releases. So what I'm going to do is I'm going to highlight only my member here as well as my CLT panel at the roof level, and I'm going to create a visibility by the selected objects. To create a new line release in the program, we can access this in our Project Navigator under the Data tab. You'll see here line releases. If I right-click, I can create a new line release. What the program asked me to do is to choose the line that this should be applied to. Well, I can graphically choose this commonly shared line, line number 31, that both the panel and this beam member share. Then I need to create a new line release type. And we can see that when we open up the line release type here, we can activate the release of the moment about the local x-axis. Now, keep in mind that the X, Y, and Z notations here refer to the local axes of the line itself. So these are not the local axes of the panel. These are also not the local axes of the member itself. So what we can do here is to also activate the slip along the line length of X, and rather than completely releasing the translation about the line length X, what we can do is to type in a spring constant here of 50 kips per foot. So what we want to do here is to also show you that nonlinearities are available. What we can do with nonlinearities, this might be applicable with the Z direction. So for example, if we have a downward deflection here of our panel onto our beam, we can set this so that it is fixed if a positive VZ. So if we have a downward deflection here in the VZ direction, then we'll see this connection fully fixed. Now, in turn, if we have an upward deflection of the panel, then we would see a fully released connection between both our beam and our panel. So that's one advantage that you can take of with the nonlinearities of line releases. Now, we won't be doing that today, so we can go ahead and uncheck this option, but instead we do want to apply the slip of the screws as well as the rotational release for our moment. So we click OK. Now the only thing I need to define here is my surface that this should be released with. And I can graphically choose surface number 63 here. I click OK. And when I click OK, I should see a line release symbol here shown back in RFEM. So now that line release is going to be applied between the member element and the panel. So exiting out of this visibility mode, we actually need to apply these line releases to all members and surfaces within the model. So another quick example would be this member we can see over here on the right-hand side. I'm going to right-click to create a new line release. And I am going to graphically select line number 20, which you can see is a commonly shared line between this member. And the line release type is already set, so I don't need to redefine that. Now, what is interesting is that this member does share two different panels. So what we can do here is to select two surfaces. We'll select surface on the right as well as a surface on the left to be released from that member. I click OK, and there is my second line release. So we'd want to continue doing so for all the rest of the members available within the model, and I'll show you that in just a minute. But let's quickly move on to the connection of the joint between our CLT panels. So exact same considerations here. These are probably going to be connected with screws or some other type of connection where maybe we want to release a moment and account for the slip of the screws. So rather than moving forward with line releases, I actually want to utilize line hinges. So I think line releases can be incredibly powerful when it comes to beam to surface connections, but surface to surface connections, it's a little bit easier to work with line hinges instead. So we can access line hinges over on the left, once again from the project navigator, but instead I'm going to go under Insert, Model Data, and you'll see here line hinges, and we can assign to the lines graphically. So we want to create a line hinge definition, and this should look fairly similar to what we saw with line releases. We want to completely release the moment. We also want to activate a spring constant for the slip along the local axes of the line. And you'll notice we have a couple more options here with rotation, but we do not have the ability to set a nonlinearity with line hinges. So that is one limitation, but perhaps with a panel-to-panel joint, you're not really working with much nonlinearity anyway. So we can click OK. So the advantage of using this assign to lines graphically is that I actually can select surfaces and automatically assign the lines. So for example, if I take a look at here, only my roof elements, I click OK. You'll notice that those line hinges were automatically applied to all of my roof panels denoted by this symbol here. And we can zoom in here, and although that was extremely beneficial, you'll notice the program even recognizes where it should not be applying line hinges if it's not connecting to another CLT panel. The problem is that with any FEA software, when we have a joint, for example, where two or more members are framing into it and all of them have a member end release, at least one member needs to be fully fixed. The exact same concept needs to be followed for 2D surfaces as well. If we have two or more surfaces framing in, we do not want to apply line hinges to the joint for all panels. We need to leave at least one fully fixed. So there's a little bit of cleanup that we'll have to go and do after we assign to all of the lines. And that includes the location here, for example, with our center panel. We would just graphically select these line hinges holding down our control key and hit delete on the keyboard. So now you can see when we are looking at the panel-to-panel connection between the left and right panels, we only have one line hinge defined. Now, if we compare that to the wall framing up into the floor, the roof panel here, this wall is considered fully fixed. So we can leave at least just one single line hinge available here. So what I went ahead and did with an already saved model, which we'll jump to it, is where I've applied all the line hinges and line releases for the entire model. So you can see all my beam members have these line releases applied, and then all of my CLT panels have the line hinges applied, with leaving at least one panel fully fixed. Okay, so that really covers the connection details of our CLT structure. The final thing to discuss before running the analysis is I'm going to launch RF-LAMINATE again. And jumping back to material characteristics, remember we are orienting these different layers in relation to the local x-axis. So the first layer is oriented 0 degrees from the x-axis, while the second layer is 90 degrees from the x-axis. So inevitably, this tells us that we have a strong orientation for each one of these panels, and that is related to the local x-axis because we have our two exterior layers here oriented along that x-axis. So what this means, if we're looking at our walls, for example, these walls are going to take some pretty heavy gravity loads. Therefore, we want to orient the strong axes to take the gravity loads. This means the local x-axis needs to be in the vertical direction. If you do not take careful note to orient these panels in the correct direction, then you're really not getting the full strength out of the panel, and it can lead to a much too conservative design. So going back to the RFEM model, what we can do here is I will activate only the wall elements by holding down my control key and selecting the vertical panels, creating a visibility by the selected objects. And I can right click on any one of these surfaces to turn on the local axes. So you'll notice that my first wall element up here on the right hand side, the local x-axis is oriented in the vertical direction. That's exactly what we want to take those gravity loads. But if we take a look at the panel right below it on this first level, the local y-axis is oriented in the vertical direction. That is not the strong orientation. Therefore, we need to make sure that we have all of these panels for our walls with the x-axis pointing up. So how can we effectively do that without having to individually rotate each panel or remodel? So what I can do is to highlight my selection box over all elements. I can double click to edit them. And here we have an axes tab. The axes tab allows us to orient the local x-axis parallel to a line in the model. So I can graphically select any vertical line. So for example, we'll choose line number 40 here. I click OK, I click OK, and now every single wall element that I selected now has the x-axis parallel to line number 40, which is in the vertical direction to take those gravity loads. Now, this isn't just limited to walls. The same concept goes for floor panels as well. So if I inverse my visibility here to show only the floor panels, we want to make sure that the x-axis is oriented in the longer span direction. So you can see for my floor panels today, the x-axis is taking that longer span. So perhaps that's okay. We don't need to make any modifications. But if you did, again, you just follow the same procedure of selecting multiple surfaces at a time and orient them in relative to a line that's selected graphically within the model. Okay, so we can right click to turn off those local axes, and we are now finally ready to run our calculation within RF-LAMINATE. And I can run the calculation directly within the add-on module. Remember from the PowerPoint exactly what this is doing. It's exporting out those global stiffnesses for our panels back out to RFEM. We're running all of the load cases and load combinations back within RFEM. And within that analysis, we're going to pull those internal forces. We're going to bring them back into the add-on module, distribute the stresses to each individual layer, and then further we're going to separate them out into tension, compression, bending, shear, and torsion stresses. So we are now presented with our results here in a table format. We can view the max stress ratio by loading. We can view the max stress ratio by surface, by composition. You'll notice here too, if I pull down my add-on module here and I click anywhere within this table, that the program automatically syncs up exactly which surface I'm looking at within the table. Now, even more so, you can see there is a big red arrow here that points out exactly where the controlling force or stress is for that particular check. And within each surface, as I mentioned, we're going to be checking bending, tension, compression, combined interactions here, shear, as well as torsion for our walls, and ultimately coming up with a design ratio. We also have the max displacements here. So this is our serviceability checks. And remember, we are running in comparison the deflections to L over 360, we will get a max ratio here as well. Now, any of this information, whether it's for serviceability or strength design, it can be exported automatically to Microsoft Excel with the click of a button here. So if we want to do a little bit further sorting. Notice as well, all the stress distributions are shown here within each layer that are automatically updated as we click within this table. We also have a parts list given to us, which is just nothing more than a material takeoff. Okay, so if we take a look at the max stress ratio by surface, I think we notice a pretty big problem. We have a max ratio of 1.81 with a big red sad face. That is because we are over the design ratio of 1.0. So what exactly could be the problem here? Well, what is nice is that rather than filtering through this huge list of information within the table, I can use these filter options here to choose all of my max design ratios, which are greater than 1.0. I click on the filter button here, and now I can see exactly where my problem areas are. You'll notice that as I'm clicking on these different high stress ratios, they seem to be occurring all at these corner locations here. And it appears that the rest of the panels really don't seem to have an issue. So this would probably flag me that this is some type of singularity issue. So let's jump to the graphics view back in RFEM. Now we're currently looking at RF-LAMINATE here. So this is the result information for the add-on module shown graphically to us back in the main program RFEM. And you can see we can switch to different load combinations that we've run. We could change the composition between floors and walls. We can select the layers, as well as view the individual stresses. Now I'm currently looking at my floors and the middle layer, and if we take a look at one of these checks here, we can turn on the ratio. And this is one of the extremely high ratios, 1.81. I can zoom in here, and like I said, the rest of the panels seem to be relatively okay, but we just have these extremely high stress peaks right here where maybe we have this beam member framing in underneath the panels, or where we have multiple wall segments kind of coming in together. And a singularity within any finite element program occurs where we just have high loads at a single FE mesh point, and it creates unrealistic peaks, and therefore we're getting high design ratios, and we might think, okay, we might need to use a larger CLT composition. But in reality, that ends up to over designing the structure simply because these high stresses really won't be experienced out in the field when this structure is actually constructed. So how do we deal with it within finite element programs? And that really comes down to the tools that you have available with the software that you're using. So I want to show you guys some advantages that we have directly within RFEM to deal with singularities. Singularities might also be very common when we have a column such as this one framing directly into a CLT panel. Again, all of the stresses are and forces are being transferred to the panel or vice versa to the column at a single FE mesh point, which just leads to no load distribution. So what I'd like to do for the singularities is to take a look at the graphic view here of only my roof panels once again. And I'm going to turn off my results, and we'll focus in on these two nodes here on either side of the beam. The first thing I want to do is to apply an FE mesh refinement. So I can right click on the node, and I can go to new FE mesh refinement. And we create a new FE mesh refinement definition here. It already recognizes it's about a node. We'll give it a radius of 2 feet. The target FE length will be 0.2 on the inner diameter, as well as the outer diameter will be 0.5. We click OK. And once we have defined this FE mesh refinement, you can see the FE mesh refinement symbol shown here. If I turn this into wireframe view and we go to calculate, generate FE mesh, you'll notice that my FE mesh is much smaller about this single node, and it transitions back into my global settings of 1 foot width FE mesh elements quite nicely. So the advantage of this is not adding in a huge number of FE mesh elements. It's really going to slow down your calculation time, but rather just focusing in on this single location here about the node. Now we also can take FE mesh refinements. We can hold down our control key and drag and drop them to different locations to make a copy. So now when I go to calculate, generate FE mesh, you can see that both of these nodes have the FE mesh refinements applied. Now this is not going to take care of our singularity problem, but what it is going to do is to make this high stress location available to us and a result in a much smaller location than rather us using, the 1 foot width of the global FE mesh settings. So we're kind of isolating the issue into a smaller area. So the second part to eliminating these singularities is to apply what's called an average region. And average regions are exactly as they sound, which we can access them here within our project navigator. Once again, we can right click to create a new average region. And with the average region, it's exactly as it sounds in that it's going to average out the internal forces over a set region that we define. The first thing I want to do is to select the surfaces this average region should be applied. So I'll turn this back into a rendered view and we'll choose all 4 surfaces here that share this common node. I click OK. I want to apply the average region at this particular node. You'll notice that the node coordinates are updated. Then I need to give the average region dimensions. And a common question is, well, how big should I make my average region? And that's really up to the engineer's discretion and your particular model. There really is no rule of thumb for how big an average region should be, but you should really look at it and make sure that the results make sense once you apply this average region, that we're getting realistic load distribution. So for today, I'm going to use a dimension of 1.5 feet by 1.5 feet. I'm going to check all checkboxes over here on the right. Now what this allows me to do is to average out all internal forces in all 4 directions over this average region dimensions. I can click OK, and now you can see we have the average region symbol shown to us graphically here within the model. So similar to FE mesh refinements, I can select the average region, hold down my control key, and drag and drop it to a different node. But keep in mind that we do need to double click to edit this average region and change the surfaces here that it's applied to. We don't want to apply it to the 4 surfaces on the left, but rather the 4 surfaces on the right for that average region, and I can click OK. So now you can see both the FE mesh refinement symbols as well as the average region symbols applied to the structure at these locations. So maybe jumping to just a simple load combination here, 1.4 dead load, let's quickly run a calculation and see how our average regions affect our results. So once this is done calculating, I'm currently looking at my results here for this particular load combination. And I'm looking at my surface internal forces in the NY direction, so the axial forces in the local Y direction. And we can clearly see with these contours, how they are affected by this average region. Notice the magnitude here of my force is 3.75 kip per feet. We have the ability over in the Project Navigator to turn off our average regions as well. Now notice that we went from 3.75 and we jumped clear up to 16.18 kip per feet. So you can see how the average regions will really smooth out those problem locations, and we get more realistic internal forces that are eventually used for our design within RF-LAMINATE. So what we'd like to do then is to utilize these average regions as well as the FE mesh refinements for the entire model. So once again, jumping to an already saved model here, I went ahead and I have applied these average regions as well as FE mesh refinements to a lot of the different joints within the model that maybe I had some issue. Now keep in mind, this is not necessary for every single joint within the model. You really only need to apply it where you appear to be having singularity issues. So I took the initiative here, applied it to many of the different joints just for completeness. And what we would do now after we have applied it to the entire model is to run the calculation with an RF-LAMINATE again. Now, you might apply all of these average regions, all of these FE mesh refinements, run your calculation, and find that your design ratio didn't change at all. And this is a two-part process. The reason why is under the Details tab, we have to tell the program under the Results tab here to apply the smooth internal forces in the defined average regions. You have to turn this checkbox on, otherwise average regions are going to be completely ignored, and this is turned off by default. So once you've applied the average regions, come in here, check on this checkbox. You can run your calculation again, and now we take a look at our max design ratios, and we see a max check now of 0.9. So that was significantly reduced of 1.81 clear down to 0.9 just by applying average regions and those FE mesh refinements rather than increasing the thickness of our panels or decreasing loads. So that is how you essentially can deal with singularities with CLT design. Okay, so going back to RFEM once again, there's just a couple other things I'd like to point out. When we look at any one of these other load combinations here, and we're currently looking at dead load, live load, snow load applied to the structure. Then keep in mind we also have the rest of our result information available to us within this Results tab. This includes for our members, we have the internal forces available to us. So if we take a look at maybe this single column, I create a visibility by the selected objects. I can take a look at the axial forces or the normal forces within this member, shear forces in both the strong and weak axis direction, as well as bending moments. This is the information that we could either take into our own design tools to do member design as well, or you can take advantage of the RF Timber CSA or RF Timber AWC add-on modules to do member design all within one program. This is also true for concrete design, steel design, aluminum. If you have multi-material elements within the same model, you can utilize some of the other add-on modules to do design as well. The other very interesting thing that we have to deal with when it comes to CLT design is, of course, the connection design. Under the Display tab, I'm going to go ahead and turn off the FE mesh refinements. Maybe I can turn off the FE mesh as well as my average regions just to make this a little bit easier to see. So with the addition of the line hinges and line releases, we now have the ability here to expand our releases tree. And this is quite powerful. If I make a selection here of just a few wall panels, and we'll turn on the visibility by the selected objects. So with the addition of the line hinges, for example, we can actually view the local deformations graphically within the model of the line hinges itself. Now, why this is powerful is because we also have the ability to view the internal forces. So for example, the axial forces, we can view shear forces at those particular joints. We can also turn on the moment, but remember we release the moment, so we'd expect everything to be 0 here. For any one of these line hinges as well, we can always right-click and go to the results diagram, and you can see in a little bit more detail exactly what's going on with these internal forces. We can change to different load combinations here if we're interested in viewing the results for those particular line hinges for different load combinations. So this is the information that we'd probably want to export out to Microsoft Excel, for example, to do our connection design. And with that, not only do we have the ability to view all of this information graphically, but if we go down here to our table, we can view table number 4 for our results. We can go all the way to the end here and turn on the line releases forces, and this is all that same information here for this particular load combination for our line releases as well as our line hinges. Again, we can export this information directly to Microsoft Excel to do our connection design for our CLT panels. Okay, so that really sums up basic CLT design according to the CSA O86 that we recently have added into the program. We'll go ahead and sum up today's webinar just with a little bit more information. I know that was always quite a bit of information on both RF-LAMINATE as well as our main program RFEM. So if you're interested to read more, certainly refer to our website at dlubal.com. We also have information on our web shop about pricing if you're interested in that. I always encourage everyone to follow us on our social media sites. So YouTube, for example, has all of our previously recorded webinars and videos. LinkedIn, Twitter, Instagram, we're always going to announce events and conferences that we're at, as well as maybe just interesting technical articles that are available on our website. So again, feel free to follow us on these social media sites. If you have any questions about today's presentation or anything else, feel free to contact us in our Philadelphia office at info-us@dlubal.com, or our phone number is 267-702-2815. So again, any questions about the presentation or anything else, feel free to contact us here. So we will have many more upcoming webinars. You can register on our website at dlubal.com under support and learning and webinars. You can also register through email. As most of you know, I tend to send out a reminder email about a week or so in advance of when these webinars will take place. So keep an eye out for that for our upcoming webinar. Many of you are also wanting PDH certificates for today. Those will automatically be emailed to all participants. These are available for participants who are here for the full presentation. That is a requirement of the states that we are allowed to present PDH certificates for these webinars. So again, if you were here for the full presentation, you will automatically receive that PDH with the email address you registered. If there were any additional attendees who watched today's webinar and you yourself did not register with your own name and your own email and you are wanting PDH, you will have to request that at info-us@dlubal.com. So again, if you watched with a colleague and you yourself did not register with your own name and email address, please request the PDH at the email address shown. And with that said, I want to thank everyone for attending today's webinar, and as always, we hope to see you at the next presentation. Thank you.